Hello friends, welcome to another lecture of quantum mechanics. Here we're going to discuss about the linear vector space in our product, dimension and basis of vector space and Hilbert space. Okay, so before we start, please subscribe to the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. Right. So first let us discuss about linear vector space. So what does it mean? So let me go to let me take a new slide here. So here you see, when we say linear vector space, the linear vector space, it is nothing but a set of vectors, sorry, a set of vectors. Suppose psi, phi, chi, and so on, right? And a set of scalars and a set of scalars, A, B, C, so on, right? Set of scalar, and a rule for vector addition and rule for vector addition. So, and rule for scalar multiplication and rule for scalar multiplication. So that means it consists, a linear vector space consists of two sets of elements. And two algebraic rules, and those are, this first one, a set of vectors and a set of scalars, and these are the two rules of vector addition and scalar multiplication. Okay, so we're going to discuss about the rules. So here you see, when we say set of vectors, so here let me give you an example. The usual form of vector we have learned till now, that is, suppose we have a point here, we have a point in this three-dimensional space, x comma y comma z, and its position vector is given by x I cap plus y j cap plus z k cap, right? So here this consists two sets, right? One is the set of vectors, that is I cap, j cap and k cap, and another set is set of scalar, that is x, y and z. Okay, and it follows two rules: vector addition and scalar multiplication, because x, y, z are scalar. But when we say vector space, it is a set of vectors. Okay, it is a set of vectors. So it is not only in 3 dimension, it may be more than 3 dimension. Okay, in n dimension, that means 100 dimension, 10 dimension. So if we imagine that way, so it consists in suppose large number of vectors, set of vectors and scalars. Okay, using those, how many vectors can be modified? Okay, so here when we say vectors in this case, So it is not necessary that those vectors will be in this usual form that we used to know. So these vectors here, maybe these vectors here maybe in matrix form, in maybe polynomial form, and maybe in functional form. Okay, and so I am clear to you. Just to make these things clear, just I have taken the example of this. Okay, it is not necessary that the vectors will be only in this form that we used to know. Okay, so it may be functions, it may be matrix, and it may be polynomials and some other forms as well. So now you say now before we go to the rules, just let me tell you one more thing. Dimensions and basis of vector space. So here you see, so here dimensions. Here if you take this example, this this vector that we used to know, this position vector, here the dimension is nothing but 3 here in this case, right? And we have 3 scalars and 3 vectors, that using those we used to represent this point using this position vector, right? So, and what are the bases? Bases are these unit vectors. These unit vectors are bases here. So similarly, so in vector space, so when we say basis, it means unit vectors. It means unit vectors. Okay. So now, so let me talk about the rules of addition. Okay, addition rule. So what are the rules to be obeyed? The addition rule applies to vectors and has properties and structure of abelian group. So first property here, if we have 2 vectors phi and psi, suppose are 2 vectors, these 2 vectors are the elements of this vector space. Okay, so of a vector space, then their sum is also a vector. This plus this is also a vector, right? Is also a vector, and it must obey the commutative rule, that is phi plus psi is equal to psi plus phi, right? And it must also obey the associative rule. Suppose we have 3 vectors. Suppose we have 3 vectors phi, psi, phi, and chi. We have suppose 3 vectors. Then it must obey the associative rule as well. That is, suppose within bracket phi plus psi plus chi, that must be equal to phi plus sum of psi plus sum of phi and chi. This rule also must be obeyed. Okay, then there must exist a 0 vector such that 0 plus, there must be a 0 vector, 0 plus phi gives or phi plus 0, that gives again phi. Okay, and there must be also an inverse vector, that is if we have psi, and there must exist minus psi for who is the sum is 0, right? So these are the rules to be obeyed. These are the rules of addition. Now let's go to the rules of multiplication that we should know here. So now let me clean this addition rule. Just got it. So now multiplication rule. The product of scalar with a vector gives another vector, right? So here if we consider psi and phi, okay, two vectors, okay, of the vectors space, any linear combination. So any linear combination suppose we have A into psi plus B into phi is also a vector. So here linear combinations means with these two vectors we have multiplied these two scalars. Here A and B are scalars. So when we say scalars, it doesn't mean that these two going to be always a real number. They may be complex as well as real. Okay, so remember that. So what is the next rule that that is distributive property of distributive property of multiplication with respect to addition? That is nothing but, suppose we have a scalar into psi plus phi, sum of two vectors, then it must be equal to a phi plus a psi plus a phi. Okay, so similarly, if we have suppose sum of two scalars into a vector, then a psi plus it must give b psi. Okay, then associative with respect to multiplication of scalars, that is a into product of b and psi, this is another rule, must be equal to product of a and b into psi, right? And for each element psi in the vector space, there must exist a unitary scalar, that is I, and a zero scalar 0, such that I into psi gives psi, or psi into I, that also gives psi, and 0 into psi or psi into 0, that must gives 0. Okay, so these are the rules of multiplication. Okay. Now let us discuss about inner product. So what is inner product? So now let me clean this first. So before we proceed further, let me tell you, here we're going to study these things as a tool which will be used in quantum mechanics. Okay, so we are not going to use it as a topic of mathematics, okay, because if you try to study in details as a part of mathematics, okay, so we're going to lose the track, because in order to study quantum mechanics, just we need these tools. So our motive is to learn how to use these tools. Okay, so for the timing, just remember as rules, these are as rules and mathematical tools that we're going to use. Okay, so now let's come to inner product. So inner product, so here you see. Now what do you mean by inner product here? Suppose we have an ordered pair of vectors that belongs to a vector space. Suppose this is the ordered pair of vectors. Now, so it must have the following properties. So in this case, this inner product of these two, it is complex number. It is a complex number. It is a complex number, remember that. Okay. And next property is inner product of these two. If you change the order of these two vectors, then these two are not equal. You have to take the complex conjugate of this changed order, right? Now see, suppose, so this is one vector. If another vector is in the form of linear combination, suppose C1 is some scalar, C1 into Z1 plus C2 into Z2. Okay, so this Z is in this form, suppose, then the inner product will be given by C1. So don't change the order, write the F first and Z, then plus C2, then again, so here G1 F Z2, right? So here C1 and C2 being scalar, and scalar doesn't mean that it's always going to be real number, it may be complex number as well. So here we are dealing with such vectors such that their inner product is a complex number. Okay, just remember that way. Okay, and then F and F, inner vector of F and F, this must be greater than or equal to 0, right? And here you see the length of the vector, so length of the vector, that will be given by mod of F, which is nothing but root over the inner product of F and F. Okay, so it must be non-negative number. Okay, this must be non-negative number. So, and here you see, if you use these two properties, this one and this one, then you can write that suppose if you change the order, if you see, this is F comma C1 Z1 plus C2 Z2. So if you change the order, then you must take the complex conjugate C1 Z1 plus C2 Z2, and F, then you must take the complex conjugate according to this property, right? So then what we can write, then we can write C1 complex conjugate of C1, then Z1 F, then plus, here it should be conjugate, then C2 conjugate of C2, then Z2 and F2 its conjugate according to this property. Now if you change the order again, this conjugate will be removed, right? C1 conjugate of C1, then if you change the order here, Z1 and F, then according to the first property, then we can write F1 Z1 plus C2 conjugate of C2, then F G2, right? So this is another property. So these are the rules of inner product. Okay, for the time being, just remember as rules that we must follow. Okay, so now you see a set of non-zero vectors. Suppose we have a set of non-zero vectors phi 1 phi 2 dot 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 up to phi n, right? Up to phi n. They will be linearly independent independent. If suppose for some scalar a1 into phi 1 plus a2 into phi 2 plus dot 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 an into phi n, if this is equal to 0, then this is possible only for a1 is equal to a2 is equal to a3 is equal to dot 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 up to equal to an is equal to 0, when these scalars are 0. Okay, so only in this case, if this sum of the products of scalars and the vectors become 0, then we're gonna say these vectors are linearly independent. Okay, now you see here, let's discuss about dimensions. As I have already told you that in this case, x I cap plus y j cap plus and z cap, here the dimension is 3. Suppose we have one more unit vector and one more scalar here term, then its dimension gonna be 4, right? So that is the concept of dimension. Okay, and basis means, as I have already told you in this case, that the set of these unit vectors are the basis. Okay, so if a vector has more unit vectors, then the set will be bigger. Okay, the basis will be the set of vectors, unit vectors. And so unit vectors are what? They are basis must be elements of the basis must be orthonormal. Orthonormal means what? Suppose we have basis of a vector space, basis of a vector space, basis of a vector space, suppose psi I. So when we say basis of vector space, so that means these are the set of linearly independent vectors. Okay, and their set is denoted by psi I, which consists psi 1, psi 2, dot dot dot, so on. So these are base vectors. We're gonna say the base vectors in the vector space. If they are orthonormal, that means the magnitude is 1 and they are orthogonal, that means they are mutually perpendicular. So you can say the unit vectors, you can compare with the unit vectors. Okay, so that's it. So now let's go to Hilbert vector space. So Hilbert space is also a linear vector space. Okay, so that means it must have all the properties that linear vector space has, and it must obey all the properties of inner products. That I have already explained. Right? Properties of inner product space are which are already discussed. Okay, so properties of inner product, and it must also have two additional properties. Those are what? So Hilbert space, this is represented by the symbol H, and it must be complete. It's complete. So what does it mean, complete? Suppose we have let me take the function suppose we have this function psi of x, which is a linear combinations of vectors from I is equal to 1 to infinity, ai psi I, sorry, phi I. Phi I is the basis. Phi I, this represents basis. And also we have psi n if the summation of the vectors from I is equal to 1 to n ai psi I, if that is the case, then this psi minus psi n tends to 0 if n tends to infinity. This condition must be satisfied. Then we used to say this H is complete. Okay. So now another condition is it must be separable. It must be separable. So what does it mean, separable? So separable means here you see mod of psi m minus psi n, it must be less than epsilon naught, epsilon, where epsilon is some positive integer. This is equal to 0. So to better understand, you can say that when we say vector space, so it is a set of large number of vectors. Okay, so in case of Hilbert space, those vectors are in a sequence. Those can be represented by a general form, and using that general form you can determine all the vectors. That is that is what all about separable. You can remember that way. Okay, so hope you have understood this. So these are the properties that we have discussed. You should know. Okay, so just we have studied these things as a tools of quantum mechanics. Okay, so hope you have understood this properties, all these properties. So if you remember these properties, okay, then only you will understand our next topic. What will be the next topic? What is the next topic we are going to discuss? So that will be easy to understand if you know these properties. So that is the purpose of learning these properties. Okay, so instead of going in details of these properties, just remember as those properties, useful properties that we are going to use in quantum mechanics. So that's how we're gonna proceed. Okay, so thank you for watching. See you in the next video.